back for a second to your high school science textbooks. If you're like me, you probably walked away from those heavy, glossy pages with a very specific, very polished image of how science works.
Oh, absolutely. The classic textbook narrative.
Right. They made scientific progress look like this, perfectly straight line of pure, uninterrupted genius, just a neat, orderly relay race where one brilliant mind hands the baton of absolute truth to the next.
Yeah, like Aristotle hands it to Galileo, and then
Galileo passes it to Newton, Newton tosses it to Einstein. It feels inevitable. It feels incredibly clean, right?
it does. It is a remarkably comforting narrative, but when you actually dig into the historical record of how research is truly conducted, that textbook image completely shatters.
It really does.
Yeah, studying the actual history of science reveals a process that is anything but a straight line. I mean, it is a messy, thrilling, and often deeply confusing human endeavor.
Okay, let's unpack this because we've been poring over your notes and research papers today, and specifically Thomas S. Kuhn's groundbreaking book, The Structure of Scientific Revolutions.
A phenomenal book.
Truly. And the mission of our deep dive today is to take all these sources and basically dismantle that illusion of the neat relay race for you. We want to reveal the revolutionary and sometimes just totally chaotic reality of how human beings actually discover new things about the universe.
And that's exactly what Kuhn does so well.
Yeah, and the core thesis, the thing that really blew my mind right out of the gate in these notes, is that out-of-date theories weren't like unscientific.
No, not at all.
Take something like phlogistic chemistry, which was the old belief that materials released a mysterious, invisible substance called phlogiston whatever they burned. For a long time, that was just accepted fact.
Right, it was mainstream science.
Exactly. Our sources make it clear that ideas like that weren't just superstitious myths that silly people believed before they knew better. They were produced by the exact same rigorous methods we use today.
That is the crucial starting point for this whole discussion, really. To understand how science actually progresses, we first have to understand how a specific scientific field starts. And usually it begins in a state of total chaos.
Total chaos! I love that.
We refer to this as the pre-paradigm stage. So before a universally accepted view takes over a field, there is no shared consensus on what the fundamental entities of the universe even are.
Because there's no guiding theory telling researchers what's important and what isn't, right?
Exactly. So all facts seem equally relevant. Early fact-gathering is basically just a random collection of data. You get these massive circumstantial natural histories. Think of Pliny's ancient encyclopedias or the Baconian histories of the 17th century.
Right.
They juxtapose incredibly complex, unusable facts with casual, everyday observations.
Because there's no filter. I mean, if everything might be important, you just write everything down. And reading through the sources, that lack of a filter is exactly why you get multiple competing schools of thought in the early days of any science.
Oh, absolutely. Early electricity is a perfect example of this.
Yeah, you've got these brilliant thinkers in the early 18th century, guys like Stephen Gray, Charles Dufay, and Benjamin Franklin, and they can't even agree on the absolute basics.
They're all running experiments, but they are constantly debating whether electricity is a fluid that physically runs through wires, like water in a pipe,
Or if it's an effluvium, which, by the way, an effluvium basically meant an invisible aura or emanation that bounces off certain objects. It was a complete free-for-all.
It really was. Without a shared foundation, every researcher is essentially speaking a different language. Take physical optics before Isaac Newton.
Right. What did they think light was?
Well, there wasn't one accepted theory. There was an Epicurean school, an Aristotelian school, a Platonic school. One group argued that light was physical particles emanating from bodies.
Okay.
Another group believed it was a modification of the medium between the eye and the object. Yet another thought the human eye itself was sending out some kind of visual ray to literally touch the object.
It's like trying to navigate a massive, sprawling city where everyone is using a completely different map. One person is trying to get around using a topological map of the hills, another is looking exclusively at a subway map, and
another is looking at a street map from 1850.
Exactly. It's total chaos until someone finally prints the definitive, modern street map. Suddenly, everyone can actually coordinate. And based on our notes, that definitive map is what Kuhn calls a paradigm.
The map analogy works perfectly there. A paradigm is an unprecedented scientific achievement that is so impressive it attracts a loyal group of followers away from all those competing schools.
It just wins them all over.
It does.
Yes.
But, crucially, it also has to be open-ended enough to leave plenty of unresolved problems for this newly formed group to tackle.
Yeah.
Newton's Principia or Franklin's theory of electricity, these are classic paradigms.
Right.
They gave the community that shared modern street map.
But I have to push back here for a second. If the paradigm is the definitive map that finally works, does that mean scientists just stop being creative? Do they just blindly follow the directions on the map from then on? Like chefs just following a recipe without adding any of their own flair?
Well, what's fascinating here is that acquiring a paradigm is precisely what turns a loose, scattered group of nature studiers into a disciplined, mature profession. They certainly don't stop being creative.
Okay.
Rather, their creativity becomes hyper-focused. Before the paradigm, every scientist had to build their field anew from the ground up in every single book they wrote.
Spending half their time justifying their most basic concepts.
Exactly. But after the paradigm, they can take those foundations for granted.
Yeah.
They stop writing accessible books for the general public, and they start writing highly specialized, esoteric journal articles addressed only to each other.
Because they finally share the same language and the same assumptions, they don't have to explain what electricity is every time they write a paper. They can just start experimenting with it.
Precisely.
Which leads us to what they actually do all day. Once the scientists have their paradigm, they don't just sit around having giant eureka moments, do they? The source text calls their day-to-day work normal science.
Yeah, normal science is best described as a mopping up operation.
A mopping up operation.
I know, it might sound surprising to anyone raised on those high school textbooks, but normal science does not aim at discovering novelties of fact or theory. It is a strenuous, devoted attempt to force nature into the performed and relatively inflexible conceptual box that the paradigm supplies.
That sounds incredibly restrictive, like they're putting blinders on and deliberately ignoring anything outside their specific box.
It does sound like that, but the restriction is actually a superpower. By focusing only on a small range of relatively esoteric problems, the paradigm forces scientists to investigate a part of nature in a depth and detail that would otherwise be unimaginable.
Okay, that makes sense.
Yeah, normal science fundamentally has three main areas of focus. The first is gathering facts that the paradigm deems particularly revealing. In astronomy, that might mean spending years meticulously mapping stellar positions or measuring the periods of eclipsing binaries.
So just getting insanely precise measurements of the things the paradigm says are important.
Right. Then the second focus is matching facts to the theory. This is where things get highly technical, often involving the construction of massive, wildly expensive special apparatus.
Like the Atwood machine from our notes.
Exactly. The Atwood machine was invented by George Atwood in 1784, almost a century after Newton published his Principia. Newton's second law of motion force equals mass times acceleration was brilliant math, but gravity makes things fall far too fast to measure accurately with 18th century clocks.
So they needed a workaround.
Right. So Atwood built this massive, near-frictionless pulley system with counterweights to deliberately slow down the acceleration of falling objects just enough to time them. The paradigm provided the math. Atwood spent a fortune building a machine to force nature to demonstrate it.
Wow.
Or look at Leon Foucault in 1850. The prevailing wave theory of light predicted that light should move slower in water than in air.
And he had to prove that.
Yeah, Foucault built an unbelievably complex apparatus with rapidly spinning mirrors to measure the speed of light over short distances in a laboratory just to prove the theory right.
So they aren't trying to find out what the speed of light is so much as they are trying to prove the paradigm's prediction is correct. And what's the third focus?
The third focus is articulating the theory itself. This means resolving residual ambiguities. It involves determining universal constants, like the gravitational constant, or establishing quantitative laws, like Boyle's law for gases. It's empirical work undertaken to make the paradigm clearer and mathematically more precise.
Okay, this makes perfect sense if we think of normal science exactly like a jigsaw puzzle. You buy a 1,000-piece puzzle, and you already know what the picture on the box looks like. You aren't trying to discover the picture.
Right, you know it's a castle.
Exactly. The thrill isn't in finding out it's a picture of a castle. The thrill is proving you have the skill, the ingenuity, and the tenacity to snap all those tiny, frustrating pieces together to actually build it. The outcome is assured, but the way you get there requires immense expertise.
That's a great way to look at it.
It actually reminds me of how modern tech engineers debug software. They aren't inventing a new programming language every morning. They are working within the very strict rules of Python or C++ to solve a highly specific, frustrating bug.
That modern equivalent is highly accurate. And this raises an important question about how scientists actually learn those strict rules, because they don't just memorize abstract philosophical rules about what the universe is.
How do they learn it then?
They learn the paradigm through what Kuhn calls finger exercises. They learn by doing. They solve problems with pencil and paper. They run standard experiments in the lab. They absorb the rules implicitly by studying the successful applications of the paradigm.
And according to our notes, because they absorb these rules through practice rather than explicit memorization, scientists in different subspecialties can actually look at the exact same thing and see something completely different.
Yes, that's one of my favorite parts of the book.
There's this wild example in the research. An investigator goes up to a chemist and a physicist and asks them a simple question. Is a single atom of helium a molecule?
And they give totally different answers.
Right. The chemist answers without hesitation. Yes, it is a molecule because it behaves like one kinetically in terms of gas laws. Then the investigator asks the physicist. The physicist says, no, absolutely not, because a single atom of helium displays no molecular spectrum.
Their experience in puzzle solving told them what a molecule must be. The chemist's paradigm is built around how substances interact and move, while the physicist's paradigm is built around atomic structure and light emission.
Fascinating.
They're both doing rigorous normal science, but their specific training creates different mental boxes.
So if they're spending their entire careers building these massive machines just to prove what they already suspect and forcing nature into these highly specific mental boxes, how do they ever stumble on something genuinely new? I mean, how does a brand new discovery ever happen if everyone has blinders on?
It seems like a paradox, doesn't it? But the reality is that this rigid, hyper-focused puzzle solving creates the perfect contrasting background for spotting an anomaly.
Because they're looking so closely.
Exactly. You only notice that something has gone fundamentally wrong if you know exactly, with microscopic precision, what you're supposed to expect.
Here's where it gets really interesting. The source text brings up a fascinating psychological experiment by Jerome Bruner and Leo Postman that perfectly illustrates how our brains handle anomalies.
Oh, the playing card experiment.
Yes. They took human subjects and flashed playing cards in front of them for incredibly short exposures, but they mixed in anomalous cards, fake cards, like a red 6 of spades or a black 4 of hearts.
Spirit don't exist.
Right. And at first, the subjects' brains just forced the fake cards into their expected categories. When they saw the red 6 of spades, they just confidently identified it as a normal 6 of hearts or a normal 6 of spades. Their brains literally wouldn't let them see the anomaly. They just fit it into the box they already had.
It's a powerful metaphor for the scientific mind operating under a paradigm. In the playing card experiment, it was only when the exposure time was significantly increased that the subjects started to hesitate.
They started to catch on.
They began to realize something was wrong. Some of them experienced acute personal distress. One subject literally cried out that they didn't know what a spade looked like anymore, that they didn't even know what color the card was. Their conceptual categories were entirely breaking down.
Total mental crisis.
Yeah.
And the notes argued this is exactly how scientific discovery works, right?
Yes. Discovering something fundamentally new is almost never a single eureka moment where a light bulb turns on and everything makes sense. It is a grueling process of conceptual adjustment. Take the discovery of oxygen. Who actually discovered it?
Well, the British chemist Joseph Priestley isolated the gas first.
Right. But Priestley's mental paradigm was built around phlogiston. So when he isolated oxygen, his brain forced it into his expected categories. He thought he was looking at nitrous oxide, and later he called it dephlogisticated air.
So he held pure oxygen in his hands, but conceptually, he couldn't see it for what it was, because his mental puzzle box didn't have a piece shaped like oxygen, so he just jammed it into the phlogiston slot.
Exactly. Or consider Antoine Lavoisier. Lavoisier realized it was a completely new gas, a new chemical species. But even Lavoisier thought it was an atomic principle of acidity mixed with the matter of heat.
Wow.
The discovery of oxygen wasn't just holding a vial gas. It was an extended, difficult process of recognizing both that something is there and what it actually is.
Yeah.
And that required tearing down the entire phlogiston paradigm.
And it's not just chemistry. The discovery of X-rays in 1895 is another perfect example of a red 6 of spades causing a crisis. Wilhelm Röntgen is in his lab doing standard normal science. He's investigating cathode rays.
Very standard stuff for the time.
Yeah, and out of the corner of his eye, he notices a barium platinocyanide screen glowing across the room. Based on his paradigm, it absolutely shouldn't be glowing. That glow is the anomaly.
Huge anomaly.
But the discovery wasn't just, oh, neat, I found a new ray. Because X-rays penetrated solid matter, they violated the known laws of physics at the time. It was a massive shock to the system because it invalidated existing lab equipment. Suddenly, every experimental physicist in Europe realized that their cathode ray tubes had been pumping out X-rays all along completely undetected.
Which is just crazy to think about.
Their fundamental equations for energy were incomplete, and they suddenly needed lead shielding just to do basic research.
X-rays weren't just an addition to the pile of existing knowledge.
Right.
They fundamentally changed the fields that already existed. They denied previously paradigmatic types of instrumentation their right to that title. When a discovery forces you to change the equipment and the fundamental equations, it is a profound disruption.
So discovering one anomaly is a major breakthrough. But what happens when anomalies start popping up everywhere? What happens when the jigsaw puzzle pieces absolutely refuse to fit, no matter how hard the best scientists in the world push on them?
When anomalies accumulate and stubbornly resist all attempts to solve them using the paradigm's established rules, the field enters a state of crisis. The rules begin to blur. The paradigm itself begins to lose its unique status.
It starts falling apart.
You start seeing a proliferation of different versions of the theory as scientists try desperately to tweak the rules to make the anomaly fit. The field starts to look remarkably like it did back in the messy pre-paradigm days.
So they just throw the paradigm in the trash the moment it stops working perfectly. They hit a wall and say, well, I guess Newton was wrong. Let's start over.
If we connect this to the bigger picture, they never lightly surrender the paradigm. They do not renounce the theory that has led them into crisis. And this resistance, as counterintuitive as it sounds, is actually incredibly useful.
Wait, how is ignoring a glaring problem useful?
Because by ensuring that the paradigm will not be easily surrendered, resistance guarantees that scientists will not be distracted by every tiny random error in their equipment. It ensures that the anomaly is real, that it is stubborn, and that it penetrates to the absolute core of the field.
I see. It forces them to really confirm it.
Right. The crisis forces the brightest minds in the world to focus all their attention on this one glaring failure. And it is during this acute crisis that scientists begin proposing competing speculative theories.
This makes me think of the Copernican revolution from our sources. Before Copernicus, the Ptolemaic system of astronomy, which placed the Earth at the center of the universe, had been incredibly successful at predicting planetary positions.
For a very long time, yes.
But over centuries, planets would drift from their expected paths. To account for these small anomalies, astronomers had to add more and more complex geometric corrections. They added circles upon circles, called epicycles, to the planetary orbits to make the math work.
And by the early 16th century, the math had become so bloated that Copernicus realized the system had become a cumbersome monster. Despite all the tweaks, it was failing to solve the puzzle of planetary precession, and calendar reform was becoming a major societal pressure.
So it was just collapsing under its own weight.
Yeah, the sheer unmanageable complexity of the Ptolemaic paradigm was a clear sign of a field in deep crisis.
It was a theoretical monster that just couldn't hold its own weight anymore. I also want to look at the crisis in chemistry in the 1770s, going back to Lavoisier. For decades, the phlogiston theory was the paradigm. Remember, phlogiston was supposed to be the invisible substance that leaves a body when it burns.
Right.
But pneumatic chemistry, the study of gases, was advancing rapidly. Chemists started roasting certain metals in closed containers, and they discovered a massive anomaly. When the metals roasted, they actually gained weight.
Which completely violates the paradigm. If burning means phlogiston is leaving the metal should get lighter. But it was getting heavier. It was a glaring red six of spades.
A huge red six of spades.
And initially, chemists desperately tried to tweak the paradigm to save it. They suggested maybe phlogiston has negative weight, or maybe fire particles enter the metal as phlogiston leaves. The rules of what phlogiston even was began to blur completely. The paradigm was buckling under the weight of the anomaly.
So we have all this tension, all this blurring of the rules. What is the resolution to this profound state of crisis?
Out of this intellectual chaos, a new theory is born. Lavoisier proposes the oxygen theory of combustion, completely doing away with phlogiston. Copernicus proposes a heliocentric solar system, placing the sun at the center.
It's a total reset.
Exactly. This is not just an addition of new facts to the old map. It is a brand new map. It's a new paradigm that requires the scientific community to destroy the old rules, redefine the fundamental facts they thought they knew, and see the world in an entirely new way.
Wow.
This shift, this deeply destructive and beautifully constructive change of worldview, is what we call a scientific revolution.
So what does this all mean for you? We started by talking about those high school textbooks that paint scientific progress as a steady, peaceful climb up a mountain of objective facts. But diving into these sources reveals that the reality is so much more human and, frankly, so much more dramatic.
It really is.
It's a series of peaceful periods of intense, rigid puzzle solving that's normal science, interrupted by terrifying, exhilarating crises and revolutions that completely tear down the old rules and rewrite the game from scratch. Progress isn't a straight line, it's a series of massive paradigm shifts.
And acknowledging those shifts requires us to recognize a fundamental truth about human perception. The way we see the world right now is entirely shaped by the paradigms we currently accept. We are, all of us, wearing conceptual lenses that dictate what we can and cannot see.
Which leaves us with a final, I think, very provocative thought to mull over. We've seen how the greatest, most rigorous scientific minds in history were completely trapped by their paradigms. We saw Joseph Priestley holding pure oxygen in his hands and being utterly unable to see it because his map told him it was just altered air.
Right.
We saw test subjects staring right at a red six of spades and calling it a heart because their brains wouldn't let them process a black suit printed in red ink. They were blinded by their own mental boxes.
Happens to all of us.
So, as you go about your week, think about this. What red six of spades are you looking blindly past in your own life? In your industry, in your relationships, or in your core worldview today? What obvious anomaly is staring you right in the face, completely invisible to you, simply because it doesn't fit neatly into your current paradigm? Until next time, keep questioning the puzzle pieces.